Hello, and welcome to this webinar presented by Paratherm Heat Transfer Fluids, which is a division of the Lubrizol Corporation. My name is Matthew, and I'll be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The large window with the heading Presentation in the upper left is the primary window for today. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now, I would like to introduce today's presenter. With us today, we have Ryan Ritz, the Global Director of Heat Transfer Technology for the Lubrizol Corporation Paratherm Division. To read more about Ryan, please look at the speaker bio window right next to the main presentation window. And Ryan, welcome to today's event. And with that, I will pass things along to you to get started.
Thanks a lot, Matt. I appreciate it. And thank you to everybody who's registered and who's either watching this with us and attending live, and those who are going to be watching it on demand. Welcome and thank you as well. So today we're going to be spending some time going through the red flags and the quote-unquote hot spots with thermal fluids and thermal fluid operations. Really just showing different ways that you can avoid major issues. So finding the minor issues before they become major in your thermal fluid system. So again, welcome to everybody. Just to run through some of the key topics that we're going to be going through today. We're going to be defining the scope of what we're talking about and just kind of setting the stage for what the tone of the presentation is going to be, what we're going to limit it to, things that we're not going to be talking about that might have similar definitions. So just really quick going through the fundamentals of thermal fluids and their operations. A lot of what we're going to talk about today, you'll see will take into account that the attendees and those watching already have a basic understanding of the technology and what they're used for. On the same kind of wavelength of that, we're going to be going through the basics of the system elements and what it takes to run these operations. And then talking about appreciating the impact of this technology, the useful side of what happens with it, the pitfalls that you can fall into, and just really understanding the overall impact of what a thermal fluid system means to the plant and its users. And as the topic goes, we're going to be talking a lot about the red flags of fluid selection. So you'll see the red flag that you see here on this slide that just popped up. That'll be showing up in some size, shape, or form throughout the slides when we're talking about pointing out the red flags. We're going to be talking about recognizing where they are, what they are. From a standpoint of this first section, we're going to be going through inadequate fluids or what we would call imposter fluids, fluids that may seem like they would be a good choice for a heat transfer system, but at the end of the day, really are going to be cause problems for one reason or another, and we'll discuss all of that. So really understanding what makes a good fluid, but then really switching it up and looking how to define and how to see what a bad fluid would be. Okay. After that, we'll move away from the fluids. We'll assume that everyone's learned how to avoid the products we want to stay away from. And then we'll move into when you're running that ideal fluid that you've chosen, the right fluid, the proper fluid, talking about when you're running it in the operation, looking for a quote unquote, and this is a play on words to go with the title, but the hot spots within the system, right? The key equipment components that you really want to focus on that cause the most problems, the ones that give you evidence up front on when a problem is going to happen and how to act on that and what to observe and how to react. So monitoring for the warning signs, looking at the cause and effect analysis, the conditions that cause the problems, the locations within that system. Again, looking at more red flags and the ramifications of not acting on those red flags. And then to close it out, before we hopefully have some time for your questions and some further discussion, we're going to look at what to pay attention to when you're long-term doing preventative maintenance, doing active maintenance on these systems, on the fluids, um, uh, what the right actions are to take, what you want to avoid, what the right kind of reporting you want to have, what to look for when you're just doing a regular maintenance type operation. Okay, so with that, we will move forward into our scope. So defining the scope, thermal fluids, also known as heat transfer fluids, also known as hot oils or thermal oils or thermic oils, really depending on which industry, which area, which location, which region in the world you might be in. These could be all interchangeably used terms for this technology. You'll probably hear me going back and forth between thermal fluids and heat transfer fluids for the most part, referring to the same thing. Regardless of what you're calling them, though, the reason for the technology, the reason why thermal fluids are useful in an operating process is that they're able to generate high operating system temperatures without really creating a lot of pressure. And that's the real big advantage, because with pressure comes complications to your operation. Increased pressure kind of decreases the safety margin, a lot more maintenance that has to go into things, a lot more complications and attention that needs to be paid to the system. So that is the positive and the negative of these systems, is that they are kind of more of a set it and forget it. It's kind of more of a low maintenance type operation, which means that while they're running, sometimes they end up getting taken for granted that some of the problems can happen. There we come in today with this presentation, how to notice those red flags and what to do and how to act on them, so they don't get forgotten in the background. The presentation scope, we're going to be limiting this today just because of the limited time we have, and we can't go into an overall scope of all the different kinds of fluids that might be present. We're going to focus on high temperature systems that operate in a closed loop. And by closed loop, I mean that they have a closed loop with an open vented expansion tank, but the loop itself is not an open bath. It's not open to the atmosphere like that. So these are going to be circulating systems, so flow is going to be very important, and you'll see we'll talk about that more moving forward. We are going to be limiting this to hydrocarbon-based heat transfer fluids, so mineral oil-based, natural organics, aromatic type synthetics. We're not going to be getting into anything water-based or aqueous. Some of the same principles are here, but the specifics are going to be a bit different with the water-based fluids. So that's really the scope of the presentation that we're going to be going forward now. Keep that in mind as we move forward, that if you're using a water glycol or some kind of a fluorocarbon type fluid, some of what I might say may or may not apply to your exact operation. So the very basics of a thermal fluid system, and this is again a circulating closed loop thermal fluid system. And we'll see this is a secondary type heating, so you're taking the thermal fluid or the heat transfer fluid, and you're heating it in a heat source, right? So here's your heat source, and as you're moving forward with the operation, the heat source will put the heat energy into the fluid, which is then piped and pumped out into a system that's going to be controlling the temperature of whatever your process user is. And that could be specific to whatever your industry is, whatever you was calling for the heat that needs the temperature control or calling for the chilling. That will be our process user. In this example, and the example that we're going to be using this flow chart for the rest of our examples moving forward, there are 3 process users. This could be 1, this could be 12, whatever the setup is, but we use 3 here just to give some examples of running the system with multiple users and some of the red flags that are associated with that. We do have our system expansion tank, which we're going to spend a lot of time talking about because there's definitely some red flags there to pay attention to. The expansion tank is the main reason that we have a system able to be operated at high temperatures with that low pressure. The pressure is relieved because the volume expansion of the fluid as it heats up has a place to go, and that's the expansion tank. So you see here it's represented there. And then obviously you've got your piping and valves, and this is a closed loop circulating system. So we have that represented with a circulating pump here, which is very important to maintain the flow of the system. So I spend a little bit of time, if you've ever been in one of my presentations or webinars before, you probably recognize the message of this slide and the contents of this slide. It's appreciating the impact of thermal fluids on operations. The reason why I use it so often in most of my presentations is because I feel the message is that important. I think one of the biggest reasons why thermal fluids prematurely degrade or cause problems, or there may be some miscommunications or some misinterpretations on their impact or their use, is because really there's not a lot of widespread knowledge on just how important and how widely used this technology is. So some of the impact considerations to think about: these systems are running hot most of the time or very cold. There is a volume of heated or some kind of oil fluid circulating, sometimes overhead, in the presence of people and objects that are going to be high capital expenditures. So protecting the people in your plant from a safety standpoint, that's really important to consider. Protecting the investment of the equipment, a really important one. There's a red flags based and associated around fluid selection are going to translate into making sure we protect the equipment that the fluid is going into. A lot of that has to go around running an efficient operation. We want to make sure that we have these fluids that are designed to do something. They're designed to pull that heat energy away from that heat source. They have to hold on to that energy as they get pumped through the pipes. And then when they get to the heated process, they have to then release that heat energy, right? So there needs to be some efficiency there that goes into play. So we need to make sure that we're running a very efficient operation, and the heat transfer fluid and the way you operate the system has a lot to do with how efficient the operation will be. And all this, again, goes around to avoiding unplanned maintenance and avoiding production downtime. So fluid selection is a very important part of that. That's why we have a whole section based off of it. We're not talking about brands of fluid here. We're not talking about any of that. We're talking about just the right design fluid, a purposeful, intended fluid to be used specifically for heat transfer, right? So we'll go through what the hallmarks of that are. Because using the wrong fluid is likely going to lead to premature accelerated degradation. That in turn is going to cause more potential for equipment failures. When you have the fluid degrading and breaking down and fouling the surface of your equipment, that will mean increased maintenance. When you have that kind of level of fouling and the changing of the physical aspects of the fluid, that'll lead to decreased efficiency. And you start to get into a downward spiral of problems that, if unchecked when they first start happening, can really cause a lot of issues down the road. Those issues are mostly intended around maintenance and operating procedures. So operating outside of your design specifications for either the fluid or the system, and failing to adhere to the basics. And we're going through the basics here because that's what's most important, right? The preventative maintenance practices that are really pretty easy and pretty standard. But if you're ignoring them and not keeping up on them, the damages that they cause to both the fluid, the equipment, are irreversible. So we're talking about a lot of expense to fix those problems that could be caused. And of course, our primary consideration is always safety. So when you're running a system properly, a properly designed system being run properly with the proper fluid, these systems are inherently safer and lower maintenance than other relatively well-known technologies such as direct heat or steam. But the inherent dangers, because they're high temperature operations, will increase exponentially if any of the factors are taken for granted and ignored. So that's what we're going to do here. We're going to give you a really quick, easy way, some really good tips, user-friendly, not too complicated. You don't need to be a technical expert to really understand the red flags that can cause the big problems. Okay. So now that we appreciate the impact, let's get into what these red flags are. Let's get into when we're looking at a fluid selection. Now, this could be multiple ways. This is a very general way to look at this, a general perspective. This could be you have a brand new system and you're searching and sourcing a new fluid for it. So we're going to give you some red flags to look out for, and making sure you don't fall into the traps of selecting the wrong product. This could be that you have an existing system and maybe you have some issues with it. Maybe you're having trouble finding the fluid, or there's just premature degradation. Maybe the responsible party before you didn't know what the red flags were and chose one of those imposter or improper fluids. So we're going to just show you what the red flags to look for there are. And then when we get into maintenance operation, we'll say, the proper ways to go about replacing them and fixing and rectifying those problems. Okay. So proper fluid selection is crucial. This is really important. There's a lot that goes into this from a perspective of how you design these fluids. There's a lot of work that goes into engineering the proper products, right? But even more so, the products that are represented on the right side of things, the higher technology, the better engineering, the purposeful, intentional fluids that are meant for heat transfer. There's a larger population of fluids that don't do all of that in the marketplace today, that have the same names, that are marketed in the same categories. So it's really important to know that you can easily make the wrong decisions here if you don't know what you're looking for. Making the wrong decisions are going to, and choosing the wrong fluids will have a great impact. Everything else that we talked about, you could run a really well-designed system strictly to its operating specifications, but if you're running it with a fluid that's not truly designed to be in that operation, you're going to have problems regardless. So it's something that's always going to be really close to whatever budget you're looking at. It's something that just takes a little bit of effort and knowledge to know what the right fluid is, and even more so what the wrong fluids are to avoid. That's our intention right here. So we're going to choose the right fluid to optimize the specifications of our operation. So knowing what temperatures we need, knowing what flow rates we need, knowing what the minimum startup temperatures that we're going to require for our environment that we're in, what our users, our process is going to be most efficient running at, what the temperature requirements are. We're going to be optimizing the equipment design. You spend a lot of money on capital equipment that's designed to run a good heat transfer fluid. So we're going to make sure you have the proper product in there. Obviously, you need to optimize your budget, right? You could have a fluid that'll last you 25, 30, 40 years, but if it's overkill for the temperature you're running at and it's way out of your budget, that's not going to be something that's really on your radar. So within your budget, there are still great options to be chosen from. So we're going to go through all of that as well. Superior fluids will feature the most effective combination of these items. Now, logically, you can tell as we're focusing on red flags, the red flags are going to kind of be the opposite of these items that are the hallmarks of a good fluid. But understanding what those are to begin with, so then we can move forward. Superior fluids will always have a higher level of purification. So they're going to be superior in terms of their quality and the quality of the formulations that they're used, the raw materials that are used. Higher purification products are always going to give you a better experience in the user end of things. Superior fluids will have a higher heat transfer efficiency. I just ran through a little bit on what a fluid is designed to do: pull heat away from a heater, hold on to that heat in the pipe, and then eventually release that heat energy into whatever the user is. That's all goes into the efficiency of the fluid. So you want to have something that's really good at doing all of those things simultaneously, the best optimized ratio of those things. And then you want something that's going to be thermally stable. That's really important. That's a big difference between any other industrial fluids. Thermal stability, specifically thermal stability of these products, is going to be crucial. How well does your fluid, does your product that you're running through this system that's designed for thermal purposes, how well does that fluid hold up to the damages, the potential damages, to the stress that a thermal energy transfer is going to put onto the fluid? That's not just important for the life of the fluid, but as a fluid gets stressed, it's going to break apart, it's going to degrade, it's going to foul the system. So a less thermally stable product will cause more damage to the equipment, more maintenance, more unplanned downtime, and really start you off in that downward spiral. And then lastly, a superior fluid will feature a strong supplier partnership. Somebody who's you're going to be dealing with, a party that's going to be an expert in the fluids, can help you troubleshoot if anything happens, has a great relationship with your equipment manufacturers and plant engineers and design engineers, and is well known within the industry. So supplier partnership, long-term investment-wise, is really important as well. So just getting a little deeper into that, our primary factors that we need to balance when we're engineering a fluid that prioritizes performance. We need to target some kind of an ideal ratio of these features: thermal stability, heat transfer efficiency, product purity. We talked about that already. We're going to talk about it again. Secondary considerations look into the expansion rate of the fluid. Helps you size the equipment, make sure that what you're putting in is going to be good for the sizing of the equipment that you have. The startup temperature. Are you going to be able to start this system up cold in the environment, in the local area that you're in? The vapor pressures of the product, the cost versus the performance. Can you maximize whatever your budget is to get the best overall performance from that product? without having an overkill for whatever your temperature requirements are. Some lower priority factors that are also usually advertised with these type of products, which you want to make sure you're not always putting ahead of any of the other. Not that they're not important, but you don't want to sacrifice any of the primary factors for any of these lower priority factors. Some of them being an overabundance of oxidation resistance. There is a fine line between where it's overkill and where it's useful. And then flash and fire points, understanding what flash point truly means and how it applies to these kind of operations. When you're talking about a high temperature operation, sometimes flash point become a scary thing. We're going to dedicate one full slide on understanding the flash point and where the red flags associated with that are. So that well-designed heat transfer fluid, those three main factors, let's focus on them really quickly and so you understand why they're important. And this is really going to build our foundation of knowledge to what to look for the red flags. Let's talk about purity. The level of purification in these fluids goes well beyond just toxicity considerations. Obviously, you want to have a user-friendly product. Depending on what your product is, your operation, your exposure to the people in your plant, regardless of any of that, toxicity is going to be a consideration that you want to prioritize. But that being said, purification levels in a thermal fluid go well beyond just those considerations. The impurities that you're removing in a purification process, a distillation process, any kind of a production process to get you the high purity fluids that you want, those impurities are actually not as thermally stable as the fluid molecules themselves, especially when you're talking about a mineral oil based product that comes and derives from a crude, right? So there's a lot of impurities in that natural oil that you're going to have sulfurs and asphaltene type products and tars and all these different things that catalyze and by themselves are not thermally stable, will break out and foul onto the equipment surfaces, will decrease the efficiency of the product and cause all kinds of problems, right? So removing those impurities up front is really important. An impurified product, an inferior purified product will still have a lot of those impurities left into it. So the degradation products are automatically going to be starting off at a downward point when you have the impure products. It's going to foul the equipment surfaces. The high operating temperatures that we're talking about here can cause a lot of problems with these, what we'll call contaminants at that point. Just kind of a precursor to what we're going to talk about with the red flags associated with that. You can really just take a look and keep an eye, and we'll have this image again. But this image here of the color of the fluid, especially when we're talking about a mineral oil-based product, color is a really great indicator. So we'll get into that when we talk about the red flags associated with impurities. Next key factor, heat transfer efficiency. This is how well does the fluid do the things that we talked about it doing. Picking up the heat from the heater through a pipe wall, holding on to it as it flows and gets pumped out through a pipe. It could be 5 feet, 20 feet, hundreds of feet away from the heat source out to whatever the heat user is. And it's got to be able to hold on to that heat. And then once it reaches that user, it's got to be able to release it. So we're calculating these efficiencies based off of the product parameters, the data points that go along with temperature changes in the fluid. So an ideal efficiency optimization will have a lower end viscosity, a higher density, a higher thermal conductivity, the ability of that fluid to be able to produce and release the heat, and the higher specific heat capacity, how well that fluid holds on to the heat as it's moving through the system and picks it up, right? So these are all properties that are really important. The higher the heat transfer efficiency, the more work that went into purposely designing a fluid that optimizes all of those data points and all those parameters across the intended temperature range of that fluid, that's going to be the efficiency. So a superior fluid will have a higher heat transfer efficiency. Again, really key point to point out here, it's not just about energy savings with efficiency in a heat transfer fluid. It's not just about how well. This means that when you're talking about heat energy being transferred, any inefficiencies in that ability to pull that heat and transfer it will go into then breaking the fluid itself down and degrading the product. That energy has to be used somewhere. So any inefficiencies will go into degrading the fluid. Degrading the fluid will cause problems in the equipment and damage the equipment and foul surfaces and plug lines and block heated surfaces from doing what they're intended to do. Create sludge, jam up your expansion tank little switches. So efficiency is mostly about how well that fluid's holding up over time, how well it's going to be protecting the investment of your equipment, ultimately the protection, your investment in your maintenance, and the safety of your people. Thermal stability, the fluid's inherent resistant to irreversible damages. Key point, irreversible damages. One of the red flags that we'll talk about moving forward is the ability to recondition fluid or not. A lot of the damage that happens due to thermal cannot be fixed by putting an additive pack in or putting some kind of a reconditioned magic dust into the product, right? These products are going through a thermal stress that's typically going to be irreversible. So once the problems happen, the fluid is usually then needs to be changed out, and cleaning and all kinds of things need to happen. So we can measure thermal stability when we're putting into the context of designing a heat transfer fluid. Thermal stability can be simulated in a lab oven. Higher thermally stable product, the inherent ability for that fluid's chemistry, the molecular bonds, the interaction between the molecules in the oil itself, whatever that formulation might be. A superior fluid will have a higher thermal stability, yielding longer fluid life and less maintenance and damage to your equipment. So let's get into some of the red flags now, okay? How do we recognize what I call an imposter fluid? A fluid that is marketed and sold as a heat transfer fluid or a thermal fluid or a hot oil that's put out there with literature. It's got a drum with a label on it that says heat transfer fluid. The name might have it in there somewhere. The literature does. The salesperson that sold it to you might tell you it's heat transfer fluid. And can it legally be used in one of those systems if you choose so? Absolutely. But when you're looking for a purposeful designed fluid that's going to avoid all the pitfalls that we're trying to avoid, give you the best combination of stability, purity, efficiency, protect your equipment, really, if we're appreciating that impact the way that we talked about before, you should only be using a legitimate heat transfer fluid. Avoid the imposter fluids. And what do we mean by that? How do we recognize them? What are the red flags? You want to avoid anything that says multi-purpose fluid, lubricating oil, industrial fluids, hydraulic fluids, transformer oils, quenching fluids, turbine fluids, petroleum lubricants. These are all terms that are associated with what you might consider to be the same classification of so-called industrial oils or industrial processing oils. They're going to be sold by the same distributors. A lot of the same larger companies might make all of these things. But what you're going to run into a lot of times is, and believe it or not, it might seem a little obvious that you don't want to use a lubricating oil as a heat transfer fluid, but it's not as obvious when you're out there in the marketplace shopping for this. These are all red flags. You want to keep an eye out for these. And how do we do that if it's not going to be on the drum won't come with a label that says heat transfer oil lubricant. The literature might not say that, but there are ways to tell, and there's ways to look for it, right? So don't be misled by marketing tricks. Don't just trust the product branding. You want to make sure you take it a little step further. A pro tip, check the SDS. The drum label can say certain things. The drum label can have branding on it. The website for the company can have whatever brand name they want to have on it. Even the engineering bulletins, it can just be the basic data and the basic description of what the product is, right? So pro tip is go a step further. The safety data sheet, the SDS for the specific product, will typically tell you a little bit more. And for example here, and this, I see this every day. This is not uncommon. You look here, right at the name at the top of the safety data sheet, it'll say thermal fluid 123 XYZ. This one we have high per therm heat transfer oil 26. Even when you go down to section 1 identification, again, the product name repeated there. But this is where you take it a step further. And this is usually where you see all those red flags at the top of this slide, multi-purpose lubricating. This is where they'll show up, right down here in the application. And usually it's a little bit of laziness or just maybe not catching this because they use the same SDS for the whole product line, whatever that oil is and whatever drum it is. They just duplicate the SDS. It'll say application petroleum lubricating oil or hydraulic. Any of those that are up there, if it's listed there as the application, you're going to be using a product that's not designed for actual heat transfer most of the time, okay? A lot of times they'll get tricky with these, or they'll think they're smooth, and they'll put an entire list of applications here. You might see all or 4 or 5 of these red flag names that I have up top there. You might see all of them listed, so they're covering all their bases. What that's just telling you is that that same fluid, the physical fluid product with whatever formulation it is and whatever the singular intention for it is, are in 4 or 5 different drums with 4 or 5 different labels somewhere that are all being used for different things. But when you're doing that, you can't actually be designed to do one thing really well, especially when you're talking about thermal fluids that are getting exposed to much higher temperatures than any of the fluids that we're talked about before that are listed up there. That becomes a serious problem, and the fluid will prematurely degrade without fail. Next red flag, lack of key data. Does the fluid supplier, so when you're in a situation where you're shopping for a fluid, you're looking at fluid, and the fluid supplier does not publish or does not supply detailed thermophysical data points. Those are the data points that change as temperature changes. Those points we talked about, remember we went back to that efficiency, that second item, high heat transfer efficiency, that's key for a good fluid. You need to have, we talked about low viscosity, high density, high heat capacity, high conductivity across the full operating temperature range, right? If you don't have access to that data, that's a big red flag, because that data is necessary to actually design a legitimate heat transfer fluid. If I'm formulating and designing a fluid and I have all these different options that I'm researching and developing, and I'm working on all these different ratios of product mixes and additives and different interactions between chemistries, if I don't understand and have the data associated with those at a minimum 4 data points, 4 physical properties across the data range, then I didn't actually do any work to make sure that this stuff will actually efficiently transfer heat. It's a very high expense. It's a very big time commitment. Most of the data that we collect when we're doing R&D and we're trying to formulate better products gets lost because we don't actually ever use it because it got disqualified. But that supports legitimacy. A supplier, a manufacturer of these fluids that is going through the investment of doing all of these things is going to be more than likely going to be a good support partner, a good vendor, a good supplier, a good partner moving forward, right? So just know that if you don't have access to the full data set that was required to design a true good heat transfer at an intentionally purposeful fluid that's designed to transfer heat, if you don't have access to that data, that means that the product wasn't actually designed to transfer heat. And I'm not just talking about the basic data that you see on an engineering bulletin, not just talking about what you see on the typical properties. Look for the full data table for all those at some degree of detail across the temperature range. Okay? They're necessary to design a good fluid. So if they don't have it, big red flag. I alluded to this a little earlier when we talked about high purity, the high purity data point. Another big red flag is in impurities in the fluid. Lower cost fluids, ones that are going to be really budget friendly, we'll call it, will usually be where you get into this area of making sure that you're not automatically starting off with a fluid that comes with inherent contaminants in it that are going to foul out and cause problems in your system. Within the budget range of those types of, we'll call dirty chemistry fluids, there's some really great options that are more purified and more higher quality that will give you better results and don't start you off behind the 8 ball right away. So color is a great indicator of that. If we're looking for red flags, color is going to be a really good one to look for, okay? Especially when we're talking about mineral oils. So really highly purified thermal fluids are going to feature colorless / near colorless appearance. It might be defined as a clear, water white, even just basically very slightly tinted. And you can see a really good example of that here. You want to avoid fluids that are going to be amber, orange, yellow, golden. All 5 of these samples in this picture here, in this image, are true out of the drum, marketed as, sold as heat transfer fluids, fresh out of the drum, new products, right? So you can see just inherently these mineral oil products, the level of color indicates a really strong indication of the impurities that are going to be in this fluid. Could those impurities be an overabundance of additives that made the color change? Yes. But don't be fooled by that either, because one of our next red flags is going to be discussing just that. So avoid fluids that have strong color indicators, any of the ones that are listed there. What if you can't see the fluid before you buy it? What if it's not listed anywhere? Again, quick check. Check that SDS for that product. Go to section 9. Look under the general information and look for the color. It'll say it right there. If you see any of these indicators, amber, orange, tinted, yellow, that's a red flag. try to dismiss those fluids, or at least look a little bit further into it and question it. As promised, let's talk about additive overload. You see a quote similar to this. Hypertherm heat transfer oil 26 is formulated using a robust additive package to optimize performance. Features anti-foaming, rust inhibitors, anti-wear, viscosity modifiers. All these things are not necessarily bad things when you're talking about high performance industrial use fluids. But when we're looking at a thermal fluid, something that's specifically designed to transfer heat, big red flags. Something like that is a big red flag. And the reason being is these are typically going to be affiliated with those imposter fluids we talked about earlier. Okay, so they're not going to mention that it's a lubricant. They're not going to mention that it's also used somewhere else as a turbine oil or quenching fluid or any of those things. But there's some clear indicators there. Those additives that they're advertising and really just putting out there pretty aggressively are designed to enhance performance for the lubricant. They're designed to make a better turbine oil. They're designed to make a better bearing fluid, whatever it might be, any other industrial fluid. They're purposeful for that. But those performance advantages they offer for those applications are pretty much meaningless in a thermal system. You don't need to worry about the foaming or the rusting, or there's no low clearance areas where you're lubricating, worrying about wear, right? And most of the time, they have a negative impact. All those high efficiency properties that we discussed earlier, the viscosity, the density, a lot of times the additive packages that they put in for intentional purposes will actually take away from the efficiency. Okay. Some additives actually have some is a pretty nice term there. Most additives have a much lower thermal stability than the actual oil that they're being added to. The base chemistry of the fluid should be what's robust, not the additive package that you add to it. Because what'll happen is the add pack that goes into that, whatever those additives are, that aren't helping you transfer better heat, are going to end up fouling out of solution, fouling out of the fluid, onto the equipment surfaces, into the solid form, plugging lines, causing all kinds of the nightmares and the downward spiral that we're looking for. So don't choose a fluid that already has those things in it. They're just as bad sometimes as the actual impurities from an impurified fluid. Again, we're talking about supplier legitimacy and a good supplier partnership. Any supplier of a quote unquote heat transfer fluid that is actively advertising these features for their heat transfer fluid, for their thermal fluid, is demonstrating a real lack of expertise in what it takes to make a good thermal fluid, because those things don't matter. So if they're advertising it like this on the data, on the literature, on their website, kind of that's a red flag to stay away from. Specialized heat transfer fluids, legitimate ones, the ones you want to start off with, those of the industry that really know what they're doing and have kind of built the legacy of this product and helped develop it and innovate it over the years. They understand that you have to purposely use anything you're putting into a formulation. You have to rely on a robust fluid chemistry, the interaction between molecules. Those are designed to meet the specific demands of actual thermal operations versus something else. All right, next red flag when selecting a fluid. If the fluid or the supplier is going out of their way to prioritize the flash point of the fluid. Here's an example of that using our example we've used so far. Hypertherm heat transfer oil 26 is specifically designed to feature the highest flash point in the industry. Now, understand flash point. Outside of very strict municipalities or regions, or uninformed kind of regulations where you're demanded and you really can't fight it, flashpoint should not be a priority. And that might sound a little confusing or out of left field to those who don't really have access or haven't had this conversation before. But flashpoint doesn't really become a huge factor in a traditional industrial closed loop heat transfer system. And when you design around flashpoint, it's a red flag. In most cases, the flashpoint is a low priority. A series of compounded failures, so ignoring all the red flags that we're going to be talking about today, letting that go on for time and time again, having negative tests, seeing some equipment failures, A series of compounded failures in a designed thermal fluid system is necessary for the conditions to come together for flash to actually mean something in a closed loop system. You've got to have an ignition source, a concentrated cloud of vapor, and a fresh stream of oxygen all coming together in a single place. And there's really nowhere that can happen unless you have a leak inside of your heater where there's an open flame and the fluid is spraying into it and there's oxygen present there. And again, it would take a series of compounded failures, that downward spiral of ignoring everything we talk about today, ignoring your equipment manufacturers, your fluid manufacturers. That's what it would take for Flashpoint to actually matter. So if you're going to prioritize Flashpoint above everything else, that's going to cause some problems. So there is a very, very high percentage of systems relative to those that don't, much higher percentage that regularly operate well above the fluid's Flashpoint without actually compromising any safety standards. Increasing Flashpoint, this is why it becomes a problem. Yeah, so it'd be great to have a fluid that's the best possible efficiency, the best thermal stability, highest purity, and also have the highest Flashpoint, but the cards just don't lay out that way. When you increase Flashpoint, when you purposely design a fluid around Flashpoint, the majority of the time, the overwhelming majority of the time, it's going to require you to have a substantial increase in the fluid viscosity. They inherently go together, right? So that's going to negatively impact. Remember we talked about efficiency, viscosity, you want a lower viscosity. So when you're purposely increasing the fluid viscosity to give yourself a higher Flashpoint, to give you any substantial increase in Flashpoint, it's going to take a much more substantial increase in viscosity. That's going to have a big negative impact on fluid flow dynamics. Fluid flow dynamics are necessary for good heat transfer efficiency, and you're ultimately going to increase the degradation rates because you're worried about a Flashpoint that doesn't actually come into play. Now, again, if your municipality or your local region or whatever it might be demands that, that's one thing. You should probably put them in touch with some fluid experts to have the conversation and see if we can change their minds. All right. So moving forward, hotspots in the equipment, in the operation. Now remember, the hotspots is in quotations. They're not necessarily always going to be higher temperature, but it's a little play on words just to fit the theme of what we're talking about today. So the hotspots in a system, the first one we're going to look at is going to be the system heat source, whether that's an electrically heated system, a fuel-fired flame system with a coil, which is going to be the most common. That's really what's meeting our scope today. Let's take a look at the red flags associated with the heater itself. So taking a closer look, the heated pipe wall or whatever the heated surface is, that might be an electric heating element bundle inside of an electric heated system. But for this example, let's look at the inside of a pipe wall. You've got a flame on the other side. Let's go back to that last slide and you can kind of see you've got that flame on the inside of a coil, right? The fluid is flowing inside of this coil and the flame is going down and it's got to go through that pipe wall to heat the fluid up, right? So that's what we're going to look for this hotspot, for this red flag. The heat source, that flamed area, electric heat element, is the area of highest energy concentration in the system. Therefore, it's the primary area where thermal fluid is most prone to thermal breakdown. That's where that thermal stability comes into play the most. Your fluid needs to be flowing at a sufficient flow, which we'll call a turbulent flow. It's got to have a lot of energy. It's got to be moving almost violently to efficiently transfer heat energy out of the heater. So turbulent flow is required for efficient heat transfer. Efficient heat transfer is required to avoid these red flags that we're talking about. So you want to avoid a laminar profile. You want to avoid that low flow areas. And what we mean by that is anything that's inhibiting the flow, whether that's your flow rate, whether that's a really highly viscous fluid, whether it's a fluid that's starting up cold and hasn't thinned out yet, and the viscosity hasn't decreased because it hasn't had a chance to slowly heat up. That laminar flow profile, all of the heat energy is going to be pulled and concentrated at the wall of the pipe, and it's going to cause a lot of problems because it's not being transferred into the fluid. If it's not transferred into the fluid, it's not going to be transferred out of the heater, and that energy is not going to be used in the process, but instead it's going to be used to break the bonds. So what we want is we want a turbulent flow profile. We want a really high flow profile. We want this fluid to do what it was designed, to take that heat energy away from that wall. We want it to pull it into the fluid itself. We want it to mix really well into the bulk of the fluid. We want that flow to be really impactful and efficient at removing the heat energy, holding onto it, and moving it back out into the system. And that requires turbulent flow, good flow, and anything that's going to take away from that flow profile is going to be a red flag. Why is that the case? Well, that high heat flux, that high heat energy concentration at the pipe wall, at the heated surface, it's not going to be conveyed into the fluid itself. It's not going to leave the chamber, and it's going to be, the flow is not going to be efficient for heat transfer. We talked about this earlier. Heat transfer isn't necessarily about energy efficiency. It's not about saving on energy costs and waste heat and all that. But really what it's mostly about is an inefficient fluid will break down faster because the energy has to be used. The energy is used breaking the fluid apart at the pipe wall. That's going to cause the molecular bonds to crack, all that heat energy. It's going to then foul onto the heater walls. When you foul onto the heater walls, it's going to create like a nice carbon shell. And you actually, I've seen it where you break that coil apart in the inside, and it looks like the pipe that was a 2-inch pipe is now an inch or a half-inch pipe because you've got a layer of carbon that was baked onto the walls of the pipe from the fluid breaking down. Imagine how that impacts not only the fluid flow, but now you've got a layer of carbon insulating the fluid, bulk fluid, from pulling and contacting the heated surface. That's creating even more inefficiencies, compounding the problem and creating that downward spiral that we talked about before. So heat source red flags. Big red flag, you have trouble maintaining differential pressures through the heater. Most well-designed heaters will have some kind of a differential pressure indicator, what the pressure going through across the heater is going to be. And if that changes or deviates, it'll set off an alarm, it'll set off a switch, it'll set off something to let you know that something affected the flow rate through that heater. And that's really important because if you don't have proper flow, that's when things start happening, where the fluid starts baking, the metal in the pipe starts getting compromised, and all kinds of issues start happening. One really good red flag that's kind of a quick everyday check or weekly check, just take note of what the exhaust stack temperature, the waste heat stack, the exhaust stack coming off of the heater, right? That's waste heat. That heat that's leaving the top of the heater is heat that did not go into the fluid. And there's a regular everyday range of temperature that should fall within normal values. If something changes significantly, a notable increase from that exhaust stack temperature from what it normally is, that's a red flag. Question that. If that heat energy that used to go into the fluid, used to go out into the system, is now escaping through the stack, something is prohibiting it from going out into the fluid, and that's a red flag that needs to be checked. It doesn't just happen on its own. If you have trouble raising your temperature set point above 215, 220, 230 degrees, that's the magic number that I hear a lot on customer troubleshooting calls. And what I try to remind people is that 212, the boiling range of water, isn't an exact number when you're in different atmospheres, different areas, different elevations, different conditions, right? So if you're around that 210 to 250 degrees and you're having trouble running and raising your temperatures because you're getting pump cavitations or pressure fluctuations, that's a pretty good red flag that there should be water in your system. That's a problem. Insufficient heat output in relation to temperature. If you have a set point that you're running and your process is supposed to be at 450 degrees, and now all of a sudden you have your set point at the right point to get to that, but now your process, even though your set point hasn't changed, is 20 degrees below what it used to be, that's usually going to be associated with something blocking the heat from going out. The fluid is degraded so much that it doesn't have the same efficiencies anymore. Question that. That's a big red flag. Because what happens is most plant operators that aren't well informed and haven't sat through me talking about this before, their automatic response to that is going to be to increase the set point of the heater by 20 degrees to compensate. Otherwise, they're not going to be producing whatever needs to be heated, and they're going to have downtime and maintenance and all kinds of issues. So the quick fix is increase it by 20 degrees just to make up for it. Well, here's the problem, that compound series of failures. The fluid degradation is subject to reaction rate laws, and those laws say that every 18-degree rise in temperature that you expose something to, that fluid to, it's going to double the rate of degradation. So now, something that was caused most likely by a degradation factor, fouling on the walls or inefficient heat fluid due to breakdown or contamination or something else, low flow, whatever it might be, that's what caused the 20-degree decrease to begin with. Once you expose that to another 20-degree increase, you just doubled the rate of that happening and cut the life of the fluid in half again, and you start to see how these things start compounding. So treat that as a red flag, act on it, talk to your fluid supplier, talk to your equipment supplier, look into it before you just decide to hit a button, because all it takes is hitting that button to increase it by the 20 degrees to cut the life of the fluid in half, doubles the rate of degradation, that doubles the amount of maintenance, that doubles the fouling onto the equipment, and exponentially you start to have problems that are going to get out of control. Let's look at the expansion tank now. We looked at the heater. The next hotspot is going to be the expansion tank. Let's look a little closer at that. Inside of that expansion tank, let's look at oxidation. This is a big problem. Fluids break down by fouling or overheating or cracking inside the heater. The other way they break down is by oxidation. What is oxidation? Well, oxidation happens inside of the expansion tank in most traditional systems, and that's because it's exposed to oxygen inside the tank. Oxygen is required. When you look at this, you have air going into the top of that vent. You've got head space in the expansion tank that now has fresh oxygen in it from the air. You've got a hydrocarbon fluid that's in the actual tank. For oxidation to happen, you actually have to have hot fluid. So heat, which we have a hot system, plus thermal fluid, we have a system running thermal fluid, plus oxygen equals oxidation. Oxidation eventually will create a lot of problems. It'll increase acid numbers, it'll create sludge and tar and all kinds of different operating errors and degradation and problems down the road. So red flags within the expansion tank. If you're telling me that your expansion tank always runs hot, that's a big red flag. If you don't have a hot expansion tank, you won't have oxidation. We're trying to avoid oxidation. So always keep your expansion tank somewhere below 180 degrees Fahrenheit at max. You want to make sure that it's as low as possible, but 180 is usually where oxidation starts to really accelerate. If you're telling me that you've got an expansion tank that, yeah, you put the investment in to have some good insulation on your system, then whoever put the insulation on actually insulated the expansion tank, big red flag, take the insulation off the tank. You want the tank to run cool. You want any heat, radiant heat that gets into the tank to dissipate. Insulation will prevent that from happening. Remove expansion tank insulation at once. Hot thermal fluid continuously flows directly into the expansion tank. Now, some design features have this with a thermal buffer tank. That's a little different. If you have a bypass valve or a warm-up valve or some kind of a valve, boil-out valve that is open during normal operation, that's going to continually put very hot thermal fluid into that tank. That's going to cause a lot of oxidation very rapidly. You want to make sure that that bypass valve is closed under normal operating conditions. If you're telling me that it's impossible to keep your tank cool because of either the conditions of your operation, you're running at a very high temperature, so the radiant heat's always going to be very high. Somebody plumbed in the expansion tank right above the heater stack and you can't control it. Under those situations, you want to make sure that if you can't remove the heat from the tank, remember it takes heat plus fluid plus oxygen. If you can't remove the heat, obviously you can't remove the fluid. So if you can't remove the heat, then you have to displace the oxygen. Take that out of the equation. And you can do that by displacing it with an inert gas blanket, usually nitrogen. So if you can't keep your tank's temperatures cool due to whatever inherent reasons, make sure that you can just remove the air and you'll never have oxidation. The low level switch, this is a really important one. There is a switch, usually some kind of a mechanical switch, a plumb bob or something, a plunger in your expansion tank that is going to, a float switch that's going to measure the level. And if it goes too low, the fluid level in the expansion tank goes too low, that's going to create a lot of flow problems. It's going to create overheating and a lot of issues. We talked about how important flow is. If you don't have adequate fluid volume, you're not going to have adequate flow. So the low level switch, if you're telling me, can't tell you how many times it sets off an alarm in the middle of the night, somebody has to go reset the system, so they end up just deactivating that switch somehow. Don't ever do that. Big problem if you run low on fluid flow. You run low on fluid volume. That's a good way to cause cracked heater tubes, and that's where flashpoint becomes a problem again. Always make sure it's functioning. Sometimes there's buildup of solids in that tank, and you want to make sure that float switch can actually move up and down. So just go up there when you're checking the temperature of that tank on a regular basis. Just try to manually move that float switch and make sure that it's actually functioning properly. Another big red flag: water. Water gets into a system, it's going to cause big problems. If you're operating above the boiling point of water, which most of these systems are, you're going to have water flashing off. You're going to have water steaming off. Water can get into the system in a number of ways, and it does not take a lot of water to cause problems. It can get in from new system components, moisture from the atmosphere, transfer pumps, drums that might be left out, and they start sucking in through the bung caps. Water causes operating nightmares. So pressure fluctuations, flashing causes very severe, violent discharge of steam and displaced hot oil volume out of the top of the expansion tank. It can damage your equipment, your expansion tank, your pump impellers. You have a lot of cavitations, all kinds of different problems with water. So listening for the signs of water, making sure you slowly operate the system and do a purposeful boil out of the water. It's very time consuming, but it's necessary for good operation. Another hotspot area is the process user. And what we mean by that is if you have 3 tanks, right, side by side, and one of them is not getting the heat that it needs, and the other 2 are, or vice versa, 2 or 3, if there's some kind of abnormality, that's a red flag in your system. Something's blocking the line or a valve isn't turning correctly, you need to act on that. Don't just ignore that. So our maintenance focus, and before we'll leave a couple minutes for questions, system observations. You've chosen the right fluid. You know all of the different hotspots in the system to keep an eye on. These are just little things that you need to do, little red flags that you can pick up on. Just know your system, observe it, monitor it routinely. Look for these sites. Is there smoke? If there's smoke, that means that fluids, vapor is releasing and oxidizing. That's an area that needs to be tightened or fixed. Is there vapor clouds? Do you see steam? If there's steam coming off the top of the expansion tank, that means that there's water in the system and you need to make sure you don't flash that off. So start controlling your temperatures. Do you see any evidence of leaks, oil puddles or staining or drips or black gunk being built up around fittings? When a system's at full temperature, things expand. You might not always see the leaks, but look for evidence of leaks, so puddles, stains, accumulations. If you have insulation that's saturated and wet, that means there's a leak, and that's a big problem. It's a fire hazard if you have insulation saturated with hot oil. Look for rusting or pitting in the bottom of your expansion tank. A lot of people think that's due to the higher acid numbers. 99% of the time, it's because water settled to the bottom of the tank. It can't escape out of the top, so it's rusting out the bottom. Pay attention for kinked flex hoses or parts that just don't have the quality or the composure that they should. They're going to cause a lot of problems down the road as well. Listen to the system. Is the expansion tank crackling? Is there banging in the system? Is that vapor? Is that some kind of a vapor or anything else trying to get released from the system itself? Listen for whistling, any high-pitched sounds, pump cavitations. Anything that's outside of the norm is a red flag. Periodically record your system readings and make sure that the differences don't change too much. So stack temperatures, gauge readings, flow rates, differentials. Monitor your temperatures. Keep checking. Shoot a thermal gun up at the expansion tank to make sure it's not running hot. Look at your flows, your pressures, and act on anything that's out of whack. Fluid analysis is going to be really important for that. Most reliable tool for keeping your system running at optimal levels. You should do it minimum at an annual basis. And after any changes, those tests should be specific. This is a big red flag. Do not trust getting your fluid analysis done for your thermal fluid by the same company that does your lube oil analysis. They might be similar tests, but the condemning factors, the condemning limits are a lot different. So what might look still passable for a lubricant oil could often be detrimental for a thermal fluid. So make sure you're getting the fluid tested by a legitimate thermal fluid lab. It's going to give you a plan of action based on whatever the options are, whatever the conditions are. Check your fluid visually when you take that sample. If you see anything with a lot of solids or chunks or very, very sooty, the viscosity is going up, the color is really dark, those are red flags. Still send it to the lab to get checked, but you should just have an idea that that fluid might need to be acted on. And then just follow maintenance practices that are responsible. When you make sure you're cooling things down before you're working with them, purge any fluid or vapors out of your pipes for welding. If you're sampling a fluid for a fluid analysis, make sure it's cooled down. Never use, if anybody comes in and tries to sell you on a water-based cleaner, even if the fluid's out and they promise you they'll get it all out, big red flag, don't do it. Too many times we've had people just completely waste new charges of heat transfer fluid because of all the water left in the system. And always wear proper PPE. So the big thing is acting on these red flags. We know how to recognize them, act on them. The fluid's going to degrade. You just need to keep an eye on it and slow it down. It's going to reduce the safety margin. It's going to create a lot more maintenance. It's going to happen over time. But our goal is to recognize these red flags, act on them quickly before they become spiral down compounded problems and minimize the rate at which that degradation happens. All right, quick question or two, Matt? Thank you guys all for your
Hey,
time.
Ryan. Yeah, thanks so much for that presentation. Unfortunately, it looks like we just ran out of time. So, to the audience, you can still send us a question right now. We're not going to have time to answer it. However, we will reach out after the webinar is over. So if you have any questions or comments, please add them to the Q&A box on your screen and click submit. And we do apologize that we ran out of time, but Ryan's presentation was just so good that we had to go the full 60 on this one. So while you're doing that, I just want to remind everybody, first of all, thank you for attending. And of course, thank you to the Paratherm team and Ryan for that great presentation. And of course, I want to remind everybody that they are going to receive an email from us with a link to the on-demand version of this presentation. So you can come back and watch this again or share it with your colleagues. And again, if you have any questions, you could just pop them in the Q&A box right now and hit send. I'll just give it another moment. And while you're doing that, I also want to remind you, if you could, take a brief survey. It will appear on your screen after we end this webinar. And then for on-demand viewers, you'll find the survey located along the bottom of your attendee console in the survey widget. Okay, thank you again, everybody, for attending this webinar event. Take care, and we will talk with you soon.
Thanks, everyone.